Hi there guys, and welcome to this video where we're going to take a look at a mathematics problem that I've chosen from this book, which I've used before in some of my other videos, but it's Further Pure Mathematics by Bostock, Chandler and Rourke. And we're going to be taking a look at some reduction formulae in this video. So, just to give you a bit of an idea about what the point of this video is, it's not to, what I'm going to be doing is I'm going to be going through a problem, finding the solution to a problem, and it's going to be my solution that I've come up with for this particular problem. It's not meant to be a model solution to the problem. It's not the solution that I've just taken from the back of the book and I'm just telling you do this, do that, do the other. What I'm really wanting to do is to kind of explain the problem solving process explore the problem solving process in a bit more detail. Okay, because one thing that I find is of great difficulty for GCSE and A-level maths students is that a lot of the material that they're presented with is in a very polished form, whether it's in the classroom, whether it's in their textbook, and this can make it difficult for them sometimes to appreciate just how much work needs to go into finding the solution to a problem. So what they see is their teacher, the teacher's got limited time, so this is no disrespect towards the teachers. The teacher has limited time, but they present a solution which is polished and it's straight to the point. Okay, it does the job, but very little consideration is often given to what motivated those particular steps to be taken. And sometimes, particularly with challenging problems, non-routine problems, what you need to do can take some time to clarify, to unravel. There's various ideas that you've got to try out beforehand before you actually get to something that works. So what I'm wanting to do is to really present that process in these videos. What motivates my ideas? What was I thinking? What kind of ideas did I try that didn't work, and how did that affect my thinking when it came to trying to find a solution to a particular problem? Okay, so if you're looking for model solutions to problems, this is not going to be the right video for you. Okay, but what I'm trying to do also is to reach out to those mathematics students who are really wanting to aim high and develop their problem-solving skills and develop their mathematical knowledge and understanding. Maybe you're looking to get into university, a high-ranking university, to do mathematics, or whatever it is that you're looking to do. They're the kinds of people that I'm wanting to help. So if you know anybody that's looking to do mathematics at university and needs a bit of a leg up, please forward these videos onto them, share these videos with them. And in the meantime, if you wouldn't mind hitting the subscribe button and giving this video a like. I don't make any money from making these videos. As you can probably tell from the very low production quality of these videos, I don't make any money from doing them. I make them because I enjoy making them. I make them for the hell of it, because I want to help you to achieve the results that you want to achieve. Okay, so if you do derive some benefit from these videos, please show your support by hitting the subscribe button and hitting the like button, and maybe leaving a nice comment as well. That would be great. So let's have a look at the problem. So it's from Further Pure Mathematics, and it's on page 425, and it's question 3. By the way, this is an excellent book if you are preparing for further maths exams, step exams, MAT, whatever it is that you're looking to do. This is an excellent book. Okay, in comparison, it's an old textbook, so it's from the early 80s, but that doesn't mean that it's out of date or anything like that. It just means that some of the content that's in it is maybe a little bit more advanced than you would typically find on a current A-level maths or further maths course. Okay, but it goes into a bit more detail with things. The problems are much more challenging, and compared to a lot of the modern wishy-washy kind of textbooks, this is definitely something worth investing in. Okay, so question number 3. So given that I of Pn is equal to the integral from 0 to 1 of 1 minus x to the power of p, x to the power of n dx, and p and n are greater than or equal to 0. Prove that for p is greater than or equal to 1, n plus 1 I Pn is equal to p times I p minus 1 n plus 1. Okay, so there's a few parts to this problem. I'm going to be possibly referring to my notes because it's a while since I did this problem, so I just need a bit of a reminder about what's involved with it from time to time. But this is what's called a reduction formula. Now, they don't get much emphasis now on the further maths course, but I love reduction formulae. They're great. I was fascinated with reduction formulae when I was doing my A-level further maths. I don't know why. There was a certain charm about them, and I really enjoyed deriving, trying to find reduction formulae for certain functions and things like that. Just kind of playing around with the various techniques. But one thing that you will often apply when finding reduction formulae is integration by parts. Okay, because with integration by parts, what you're doing, if you remember, you've got u times dv by dx equals u times v minus the integral of v times du by dx. What you're doing is you're kind of shifting the derivative from one function to another, and I liked this idea. I really liked this idea doing A-level maths. Again, I don't know why. It just seems almost too good to be true that you could just shift the derivative from one of the functions to the other, and this made it possible to made the integral easier. Okay, I mean you do pay a price for it in a way, but the fact that you could do that was for me that was quite fascinating. Well, that's what we're going to be doing here. Now, one of the things when it comes to using integration by parts, which is something that a lot of people struggle with integration by parts, is actually making a decision about how you're going to assign the functions u and dv by dx. I mean, first of all, you've got to remember that it's u and dv by dx that you assign, not u and v. So pay attention to formulae. When you're given formulae, I'm sure you know this, but just a quick reminder, pay attention to formulae. Because formulae are meant to clarify what you need and what kind of expressions or quantities you need and what to do with them, right? And so many people just overlook this. They just don't read formulae. They look at formulae, they might know them off the top of their head, but they don't really appreciate what the formula is telling them to do. So you've got to take a bit of initiative when it comes to using integration by parts, in that you have to decide which of these are you going to assign u to, which are you going to assign dv by dx to. Now, generally speaking, what you want to do is assign dv by dx to the thing that is going to be a bit easier to integrate, and u to the thing that is going to be a bit easier to differentiate. If there is such a thing, that might not always be the case necessarily. But that's what you might try to do. Or because you're going to be differentiating u, you want to see u get simpler when you differentiate it. So the expression for du by dx, generally speaking, you will want it to be simpler than u. And when you integrate dv by dx to get v, you don't really want it to get much more complicated than it already is. Okay? There are exceptions to this. So when you use integration by parts, for example, to integrate natural logarithm of x, you might have to break this rule a little bit. There might be certain instances where it's justified and it just works to kind of do the opposite to what this rule of thumb states. Okay. So how am I going to assign u and how am I going to assign dv by dx? Well, I'm going to assign u, and if you're not sure, you just got to try it out, right? u to 1 minus x to the power of p, and dv by dx to x to the power of n. Now, I probably chose these because it's easier for me to integrate this than it is to integrate this. I can actually integrate both of these. I'm sure you can as well. It's not exactly some sort of superpower, but it just seems to be a little bit easier for me to integrate this thing. So what do I get? I get du by dx is equal to p minus p, 1 minus x to the power of p minus 1. Also bear in mind that I'm looking for I, p minus 1, n plus 1. Okay, and v is going to be equal to x to the power of n plus 1 over n plus 1. So I, p, n is going to be equal to u times v, so 1 minus x to the power of p, x to the power of n plus 1 over n plus 1, and that's, don't forget the limits between 0 and 1, minus the integral from 0 to 1 of, so I've got u dv by dx, so it's going to be v times du by dx. So it's going to be plus p times 1 minus x to the p minus 1, x to the power of n plus 1 over n plus 1. So that's going to be equal to 0. So we get IPN is equal to p over n plus 1. So I can pull constants out of the integral. Integral from 0 to 1 of 1 minus x, p minus 1, x to the power of n plus 1. This is looking good, which is p over n plus 1, I, p minus 1, n plus 1. So all it would be then is just multiply both sides by n plus 1, and I get the result that I'm after. Okay, so nice, easy application of integration by parts. Okay, so then I'm going to have to clear some space. Going further to show that p plus n plus 1, IPN is equal to p times p minus 1n. Okay, so this is again kind of an integration by parts, I think. So I just need to refer to my, like I said, I did this a while back, so I'm just got to kind of refresh myself a little bit on it. So what do we get? P minus 1. Aha, right, yeah, okay. So IPN is equal to the to this integral. But I think what gave me the motivation to do what I'm about to do is the fact that I've got p minus 1 here and n. Okay, so I know that when I use integration by parts on this, that kind of reduces the power in one and increases the power in the other. Here I've just reduced one of the powers. Okay, so what I did was wrote 1 minus x to the power of p as 1 minus x to the power of p minus 1 times 1 minus x times x to the power of n, which is the integral from 0 to 1 of 1 minus x, p minus 1, x to the power of n, minus, or dx, minus the integral from 0 to 1 of 1 minus x to the power of p minus 1, x to the power of n plus 1. Okay? Because then I've got IPN is equal to, this is I p minus 1n minus this here is I p minus 1 n plus 1. Okay, here I p minus 1 n plus 1. So that's equal to n plus 1 over p I of pn using what we've just proved here. And then it's just a multiply through by p. So we get Pn equals P minus 1n minus n plus 1 I Pn. Add this to each side, then you get, and I want to write it in the right order, P plus n plus 1 I Pn is equal to P minus 1n. Okay. So this is quite a common thing to do, I guess, in some contexts. Actually, be aware of the fact that 1 minus x to the power of p can be kind of split up in various ways. I'm not saying that you always need to do that, but it is something that's going to be potentially quite useful to you from time to time. Now, this is a really useful reduction formula because what this means is that I can gradually decrease the power p until effectively I get to 0. So that's what we're going to be doing now, because what we're asked to show is, let me look. So hence prove that if p and n are positive integers, that I of Pn is equal to p factorial n factorial over p plus n plus 1 factorial. Okay, so what we know is that p plus n plus 1 I Pn is equal to p minus 1 n. Okay, but I p minus 1 n in turn is, so we've got p minus 1 plus n plus 1 is equal to p minus 1 I p minus 2 n. So you can see how I can gradually reduce the power p, or this index, should I say. So okay, I can actually replace the p minus 1 n here with a suitable expression over here. So in other words, I get I forgot my p plus n plus 1 I Pn is going to be equal to p times p minus 1 over p plus n. So it's p minus 1 plus n plus 1, so cancel, p plus n, I p minus 2n. So I can just kind of rearrange this a little bit just to make it a little bit easier for me to deal with. In fact, I'm actually going to leave this as p plus n plus 1 minus 1. So what do we get? We get I Pn is equal to p times p minus 1 over p plus n plus 1, p plus n plus 1 minus 1, I p minus 2 n, which in turn is going to be equal to p times p minus 1 times p minus 2 over p plus n plus 1 times p plus n plus 1 minus 1 times, p plus n plus 1 minus 2 I p minus 3n. Okay, so then I'm going to have to think, I'm really wanting to go down to I0n. Okay, so I0n. What am I going to have here as my multiplier once I get down there? Well, notice that here I've got p minus 2, here I've got p minus 3. So if I've got 0 here, I'm going to go from p minus 1 all the way down to times 2 times 1. Okay, this number is always 1 greater than this number, evidently. That's the pattern that I spot. So then down here I've got p plus n plus 1. How many steps have I gone down? So I've gone from p minus 1 to 0. That's p minus 1 steps, right? So I started at p plus n plus 1, so I'm going to go down to p plus n plus 1 minus p minus 1, which is equal to, well, that's p factorial over p plus n plus 1 down to, there's going to be some cancelling here, p1 over n. Sorry, no, minus, that should be in brackets, so that doesn't cancel. That was, I'm glad I spotted that. So that's going to be n plus 2. Okay, so, I not 0. Not 0, 0n. I0n is equal to the integral of just x to the power of n from 0 to 1, using this formula up here. So I get x to the power of n plus 1 over n plus 1 between 0 and 1, which equals 1 over n plus 1. So in other words, this is equal to p factorial over p plus n plus 1 down to n plus 2. Now I've got this is equal to 1 over n plus 1. So what can I do? Multiply numerator and denominator by n factorial, and that gives me p factorial n factorial over p plus n plus 1 factorial, which is what I need. Okay. So this is one of the great things about reduction formulae, is that you can take these really complicated integrals and you can gradually reduce them step by step. And you can do this to great effect with some trigonometric functions, powers of trigonometric functions. For example, you can find reduction formulae for sine to the power of nx, or cos to the power of nx, and things like this. And you can integrate these much more, well, in fact, you barely even have to do any integration. Once you get right down to the end case, you find that the integration is almost trivial. So, that was, it's a bit messy. That's how it is sometimes. Hopefully you understand what I've done here with the factorials, that you're familiar with factorials. By multiplying the numerator and denominator here by n factorial, I'm just kind of completing this here in the denominator. And yeah, that's it. So, good stuff. That brings us to the end of this problem. Hopefully you understood what was going on. If there is anything that you didn't understand, please feel free to ask any questions that you've got in the comment section. I'll be happy to help you. And with that, I'm going to finish this video. Thank you very much for watching.